Hi, my name is Matteo Mazzotti and I am a research associate working in the WaveLab of Professor Massimo Ruzzena at the University of Colorado Boulder. In this video, I'm going to present an experimental and numerical analysis of lamb wave transmission through the coronal suture of a dry human skull. There have been some studies recently that demonstrated that the human skull can sustain a guided wave motion, and it has been suggested that cranial lamb waves can be used to enhance the transcranial ultrasound transmission, to measure intracranial pressure, and also that they are responsible of bone conduction. But these studies assume that the cranial lamb waves can propagate between two far regions of the skull without taking in consideration that the cranial sutures may act as a screen for these waves. So our research group has recently started to investigate the transmission mechanism of cranial lamb waves across the suture of the skull. And what we want to do with this work is to propose a simplified modeling approach of this mechanism and also a method to retrieve the mechanical properties of the cranial sutures. The first step of our analysis consists in constructing a dispersion model of the cranial bone. In our study, we modeled the cranial bone as an infinite layer plate in plane strain, and we calculate its dispersion properties with a semi-analytical finite element method, which from now on I will just call SAFE. The SAFE dispersion relation that you can see here has the form of a polynomial eigenvalue problem where we have a stiffness operator K, a mass operator M, frequency F, wave number K, and the eigenvector U, which gives the model shape of our guided wave mode. All of these quantities depend on the bone layer thicknesses, which are indicated with T, and the mechanical parameters of the cortical and trabecular layer M. Knowing the geometry of the bone and its mechanical properties is very important because we need them to compute the correct dispersion relations. In our study, we follow a procedure that we recently published in which the thicknesses of the different layers are first obtained from CT scans, while the density, the Young's modulus, and the Poisson ratio are obtained from by matching the SAFE dispersion curves with those obtained using laser vibrometry and the matrix pencil method. From the dispersion spectrum, you can see that other than the fundamental anti-symmetric mode A0 and symmetric mode S0, we have several higher order modes. In our analysis, these are only used to retrieve the mechanical properties of the cortical and trabecular bone, but for the transmission analysis presented in our work, we will just limit ourselves to frequency ranges in which only the A0 and S0 modes are present. Now, if we want to introduce the suture in the SAFE model, we can think to cut our bone waveguide along the Z-axis and then connect the left portion of the bone to the right portion of the bone with a set of distributed compression springs that we call Kn and the shear springs that we call Kt. After we have performed the cut, we use the model expansion method to reconstruct the reflected field in the left portion of the bone as a function of the incident field, the displacement and stress eigenfields computed from the SAFE, and the unknown reflection coefficients R. And then we do the same thing on the right portion of the bone, where we reconstruct the transmitted field as a function of the unknown transmission coefficients T. To find R and T for each guided wave mode and for a given incident wave field, we require that the boundary stresses along this boundary and along this boundary must be equal, which translate into this equilibrium equation in which we can substitute the two model expansion equations. And that basically brings us to a system like this one, which we can solve for T and R in a least square sense. The next step consists in choosing an appropriate law for the spring coefficients Kn and Kt, but any assumption that we make in this sense depends on the operative frequencies and wavelengths. For example, here you can see the variation of the wavelength of the A0 mode that we measure experimentally when we go from 275 kHz on the right to 100 kHz on the left. And at 275 kHz, we have that the wavelength of the A0 mode is about 5 millimeters, while from the CT scans, we have found that the average width of the suture is about 3.5 millimeters. So in this case, we will most likely require a law for Kn and Kt that is thickness and frequency dependent. But if we work at 100 kHz, then the wavelength of the A0 mode is about 15 millimeters. So in this case, we can assume a simple mechanical law for the suture like the one shown here, where we have that Kn and Kt are directly proportional to the mechanical parameters of the cortical bone and inversely proportional to the width of the suture. And in addition to that, we also introduce the reduction coefficients alpha n and alpha t that we use to take into account the non-perfect contact between the frontal and the parietal portion of the cranial bone. Now that we know how to calculate the transmission coefficients numerically, we need a method to calculate them experimentally. And in a typical experimental setting like the one shown in this slide, we usually generate multiple guided wave modes at once, but we cannot use all of them concurrently. What we do instead is that we interpolate different scan lines from a global surface scan, as you can see here, and then we use filtering techniques in the frequency wave number domain to isolate the modes for which we want to extract the transmission coefficients. For example, as you can see here, for the A0 mode that is being extracted from this raw space-time velocity array. Once we have the filtered arrays for each line, we calculate the frequency spectra of the incident and transmitted wave packets before and after the suture. For example, this blue line here is the fast Fourier transform of the incident A0 wave packet that is measured at the location 1 before the suture. And the red line here is the fast Fourier transform of the transmitted A0 wave packet that is measured at the location 2 after the suture. So if we want the transmission coefficient of the A0 mode, we just divide the red line by the blue line frequency-wise. And this procedure can be applied for each line and for each guided wave mode of interest. Now we have two tools. One is the safe model and the other one is the experimental analysis with mode filtering. And we can use them to calculate the theoretical and experimental transmission coefficient. Now, if we want to find the experimental values of the unit coefficients alpha n and alpha t, we can combine these two tools and construct a least square problem like the one here, in which we minimize the discrepancy between the experimental and theoretical transmission coefficients with respect to alpha n and alpha t. When we solve the minimization problem, we can leverage these maps here, which show the variation of the transmission coefficient with respect to alpha n and alpha t, and for different combinations of incident and transmitted A0 and S0 modes. For example, from the map in the upper left, we can see that the transmission of the S0 mode does not depend on the choice of alpha t, and that when the S0 mode crosses the suture, there is no mode conversion into A0, as we can see from this map. And the same is also true when the A0 mode crosses the suture, as we can see here, in which case there is no conversion into S0 mode. And from the last map here, we can see that the transmission of the A0 mode depends on both alpha n and alpha t only when the value of alpha n is higher than 0.4. So a good strategy to solve the optimization problem is to use the S0 mode first to find alpha n, and then when we found alpha n, we can fix it and use the A0 mode to find the alpha t. Before to analyze the experimental data, we performed a test in which we modeled the cranial bone using geometric data from the CT scans and the mechanical data for the cortical and trabecular layers that we previously obtained from our dry skull specimen. The numerical test is a finite element time transient simulation in which we set both alpha n and alpha t equal to 0.05. As you can see here, when we apply our procedure using the S0 mode, we find an error that is about 16% on the identified alpha n and 4% on the identified alpha t. So these two errors may appear as large for a numerical benchmark, but we have to consider the fact that in the safe model, the gap at the interface is infinitesimally small and the springs are massless. While here we have tried to replicate a real suture with a finite width of 3 millimeters and a continuous distribution of the mechanical parameters. So in this sense, we still consider these results acceptable for a preliminary study. Now we can have a look at how our procedure performs when we use real experimental data. Here we have generated the transmission maps in the range that goes from 90 kHz to 110 kHz for the S0 mode and the A0 mode, and for 20 different interpolated line scans inside this scan sector. The first thing that we notice is that the transmission of the S0 mode is generally much lower than that of the A0 mode. So this indicates that the coronal suture of this specific skull specimen allows for a better transmission of modes that have a prevalent shear component. When we plug the experimental transmission maps for the S0 mode and the A0 mode into the identification algorithm, and we solve with respect to alpha n and alpha t, we find that the theoretical transmission maps for the S0 and the A0 modes are in very good agreement with the experimental maps. So this indicates that the simplified law that we adopted for Kn and Kt is appropriate for this specific frequency range and wavelengths. In this final slide, we can observe the variation of Kn and Kt when we move from point A to point B along the coronal suture. And in particular, we can see that these values are included between 100 and 1000 kilonewtons per square millimeter, and that the values of Kt are generally higher than those of Kn, which reflects the fact that the A0 mode is transmitted better than the S0 mode. Thank you for your attention, and we hope to see you again on the WaveLab YouTube channel.